Good evening, everyone. Today I will be presenting on Principal Component Analysis or PCA. PCA is a very powerful technique in data science and machine learning that helps us simplify large and complex data sets while still keeping most of the important information. So, what is PCA? PCA basically principal component analysis is a statistical technique used for dimensionality reduction. It transforms high dimensional data into a smaller one a smaller number of new variables called principal component while retaining most of the variations of for or information present in the data. And why do we need PCA? When datasets have too many features, they become harder to analyze and visualize. PCA helps by reducing redundancy and noise. It also makes it possible to visualize data in 2D or 3D and speeds up machine learning algorithm by reducing the number of features. So, let's take some real life examples. Like there is a face recognition. Images have thousands of pixels, but PCA reduced just a few principals component while still recognizing the face. In finance, stock data has many indicators, but PCA can reduce into a few major trends. Similarly, in genetics, researchers use PCA to simplify very large DNA datasets. Work step by step. First, we standardize the data so all the features are on the same scale. Second, we compute the covariance matrix to understand how features vary together. Third, we find eigenvalues and eigenvectors which represent directions of maximum variance. Then we sort eigenvalues, select the top ones, and finally transform the original data into the new principal component. So, so here is the visual intention. Imagine you have a data of two dimensions. PCA rotates the axis so that the first new axis or principal component captures the maximum variance and the second component captures the next largest variance, and it is always orthogonal to the first. This continues for more and more dimensions. So to understand PCA To understand PCA mathematically, let's break into step by step. And here we will start mathematics of PCA. So first we compute the covariance matrix which captures how features vary together. The covariance matrix is given by this C slash C is equal to bracket 1 slash n minus 1 bracket into x to the power t and x. So next we have eigenequations. We solve the eigenequation Cv is equal to lambda v, where here lambda are the eigenvalues and v are the eigenvectors. These eigenvectors represent the directions of maximum variance, while the eigenvalues represent the magnitude of that variance. Now we sort the eigenvalues in the descending order, and here is the order eigenvalues which is in descending order. So, like lambda 1 is smaller or equals to lambda 2 and so on. The eigenvectors corresponding to the largest eigenvalues become our first principal component and so on. So finally, we form a projection matrix from which we form a projection matrix, yeah, and from this eigenvectors and project the original data set z is equal to x into w, which reduce the dimensionality of the data sets while preserving maximum variance. So let's work through an example with the data sets a small data set of 5 two-dimensional points. The data set is shown here. So step 1, we will calculate each of the mean of each mean of each column The mean vector is approximately 2.04, comma 2.24. We subtract this mean from each data point to center the dataset. After subtracting the mean vectors, we get the center data set, which is 0.46 and etc. Here, which is shown here. And centering is very important because PCA works on variance, and variance is always measured relative to the mean. And first, in step 2, we compute the covariance matrix. For this dataset, the covariance outcome comes out to 0.6 0.616 on the diagonal from the first variable and 0.716 on the dimension of second variable and 0.615 on the off diagonal, showing the strong positive relationship between these features. Now we solve for eigenvalues and eigenvectors of the covariance matrix. The eigenvalues are 1.28 and 0.049. The first eigenvalue is much larger, which means principal component explains most of the variance. The corresponding eigenvectors are direction in which the data is spread out most. Here we point in the direction maximum variance, while V2 point in perpendicular direction. So, to decide how many components to keep, we look at the explained variation ratio. In this example, the first component explained about 96% of um, variance, while the second one explained only 4% of the variance. So if we want to reduce dimensionality from 2D to 1D, keeping just the first component still captures almost all the information. Now, finally, we will use two datasets. For a small manual dataset to demonstrate step by step, and second, the famous iris dataset from Scikit-learn. And as you can see in this code, here is the code I have written in the same PCA demo.py, and here is the here is the code for a small data set with a small data set, and from here it is part 2, which is iris data set. And iris data in the small dataset example in this small dataset example In this small dataset example, we saw the covariance matrix, eigenvalues, eigenvectors, and projection step exactly as we calculated by hand. For this and for the iris dataset, PCA reduced the four features to two principal components. When plotted, we can clearly cluster of the data points that correspond to different species of iris flowers. This shows how PCA can help us visualize high-dimensional data into 2D and 3D. Now, okay, in this small dataset example, we saw covariance matrix, eigenvalues, eigenvectors, and projection step exactly as we calculated by hand. And for iris dataset, when I close this, it automatically shows iris dataset. And for this dataset, PCA reduced the four features to two principal components. When plotted, we can clearly see clusters of points that different correspond to different species iris flowers. This show how PCA can help us to visualize dimensional data into 2D and 3D. And to summarize, PCA involves centering the data, computing the covariance matrix, finding eigenvalues and eigenvectors, and sorting eigenvalues to choose principal component, and projecting the data into new subspace. So PCA is widely used in data science, machine learning, and pattern recognition for dimensional reduction and visualization. And also and like PCA has some clear advantages. It reduces complexity, remove noises, and make data visualization easier. However, it has also some limitation. Like we know that everything has advantage and disadvantage at the same times. Likewise, PCA has some limitation. The principal components themselves are not always easy to interpret. PCA only works with relationships, and it is very sensitive to scaling of data. So to summarize, PCA is a very powerful dimensionality reduction technique, and it find a new features called principal component, and that gives maximum variance while reducing noise. And PCA is widely used across the data science and machine learning to make complex data simple and useful. So thank you for listening. I hope this gives you a clear understanding of principal component analysis, and I will be happy to take any questions from you. So thank you so much.